Vivekanand,
Present, sir.
Yadav,
Yes, sir.
Yuvraj.
Present, sir.
Okay, so the absentee today is Abhish Kumar.
Yes, sir.
And welcome back. I hope you would have done your quiz 2 much better than quiz 1.
Yes, sir. That is what we are trying
Okay,
to
are there
answer.
any questions related to quiz 2? I will take a week time, correct, and send it to you. And though for those who have taken online, for in-person students, you can collect the answer scripts when you are visiting IITM.
Yes, sir.
Any questions related to the quiz?
I think everybody done better than last one, sir. That is what the feedback. And most of the people are attended 100%, sir. No time issue right now, except me.
Okay, so all the questions you people have attempted, and there is no problem related to the shortage of time, right?
Yes, sir. Only 5 minutes I asked for this. That's all.
Okay, so I have given additional time also this time.
Yes, sir.
Yes,
Thank you.
yes, sir. Yes, sir. Thank you so much, sir.
Yeah, welcome.
Sir, Sabi just joined.
Who is that?
Sabish, sir. Sabish.
Okay. All are present today.
Yes, sir.
Okay, so welcome back. We are in the first chapter of the second module, emission module, which is about pollutant formation in SI and CA engine, factors affecting emissions. So here, so far in this chapter, we have discussed about the types of pollutants. So we have various species emitted from IC engine, SI and CA engine. Among those species, 4 of them are designated as pollutants because of the health effects they create. Out of 4, 3 are the primary pollutants emitted from spark ignited engine, and diesel engines or compression ignited engines emit 4 species, pollutant species into surrounding ambience. So these species create various health effects. That is what we have discussed in the previous classes. And because of the health effects, some of them also create fatal effect. Because of these health effects, these species are designated as pollutants. We need to carefully monitor the concentration of these species let out by IC engines into surrounding ambience. That's why we have stringent emission mandates in different countries, including India. We check the concentration of these species emitted from the engine before they are let out into atmosphere. In fact, if you look at the current emission mandates, which could you please mute your mic? I am getting some feedback from one of you. Okay, thank you. So if you look at the current emission mandates, which we are going to discuss in the last chapter of this module, we are almost moving towards zero pollutant vehicle. Zero pollutant vehicle, the levels of pollutant concentration are almost equal to 0. Okay, so it is also challenging considering so that's why we use the word stringent emission mandate. We use the word stringent emission mandate because it's almost like 0 level of pollutant. So it's challenging from the research and development perspective of an engine, IC engine, to achieve almost 0 level of pollutants. So there are several methods available to control the pollutant and achieve almost 0 level, but it's challenging. So in the next chapter, we are going to discuss about the control methods, pollutant control method. Nevertheless, due to the health effects created by the pollutants, we are restricting the concentration of these 4 species to almost 0 level. Then we discuss about the sources for pollutant formation for SI and CI engine. The sources are different, especially unbound hydrocarbon sources are different because it is based on the boundary layer fluid dynamics, as we have discussed, unlike NO and SIBO, which are primarily governed by kinetics, chemical kinetics. Unbound hydrocarbon formation is governed by boundary layer fluid dynamics. So we have discussed about the various sources that create pollutant formation during an engine operating cycle in a spark ignited engine and compression ignited engine. Now, having understood the sources, we are currently discussing about the mechanism. What is the mechanism upon which these four species are formed? So we have in the previous class started with the discussion on formation mechanism of oxides of nitrogen. When I say oxides of nitrogen, you have NO and NO2, among which NO concentration is very high in SI engine. NO2 is negligible, less than 3%. In diesel engine, NO2 concentration is also high, up to 10 to 30%. The rest are NO. So I will continue my discussion on this pollutant formation mechanism about NOx formation mechanism, which we started in the last class. So we have here this two species, NO and NO2. Okay, so we are going to see about the mechanism, pollutant formation mechanism for NO and NO2. NO, there are three routes as we have discussed. Three routes. There are three ways by which NO can form in an internal combustion engine, both SI and CI engine. The first one is a major dominant one, as we discussed. This is a thermal NO, wherein around 90% of the total NO is formed through this route, thermal route. Okay, and this source for forming thermal NO, as the name itself implies, it's thermal NO. So high temperature bond gases is a source for forming thermal NO. When you have higher temperature prevailing in the engine cylinder, it is going to cause this thermal NO, which is a major source for NO. Okay, and you know, NO formation is to form NO, you need nitrogen and oxygen. And air has both nitrogen and oxygen. Okay, air has 79% nitrogen and 21% of oxygen. So fuel is not the source for thermal NO, rather it is air because it contains both nitrogen and oxygen. But only favorable feature here is in air, nitrogen is a stable molecule because nitrogen consists of triple bond. Okay, one nitrogen atom is connected with another nitrogen atom through a triple bond. Because of this, it's very stable molecule. We use the word stable molecule. We also call this as an inert species. Nitrogen, from a chemistry perspective, this is referred to as an inert species because it's very stable. It won't undergo chemical reaction readily. This is one favorable feature that restricts the NO formation in internal combustion engine. Nevertheless, this is a major source. Thermal NO is a major source. Prompt NO formation takes place within the flame zone. Flame zone, you know, it's a chemical reaction zone. So within the flame, you have around 5 to 10% of NO formation is taking place, not significant compared to thermal NO. And the third one is fuel NO, which is almost negligible, primarily because the source for fuel NO formation is nitrogen contained within the fuel. So we use the word fuel-bound nitrogen. The nitrogen contained within the fuel is a source for fuel NO. One favorable feature here is fuel, gasoline or diesel. Gasoline doesn't contain any nitrogen at all. Diesel contains some nitrogen, but its concentration is found to be less than 0.1% by volume, less than 0.1%. You can imagine it's very, very low. That's why the contribution of this fuel-bound NO to the total NO is negligible, as indicated here. But one other important feature in fuel NO formation, unlike thermal NO formation, is fuel-bound nitrogen is very active until the nitrogen, unlike the nitrogen contained in the air, the nitrogen contained within the fuel molecule is very active. It can form NO at relatively lower temperature compared to thermal NO formation, which takes place through the air route. Through air, this is forming. This happens at high temperature, whereas the fuel NO is very active. It can oxidize at relatively lower temperature and form NO. So basically, nitrogen is oxidizing to form NO. Okay. So in thermal NO formation, we have three important reaction steps as we discussed in the previous class. This is put together. These three reactions are called extended Zeldovich mechanism. Zeldovich is a German engineer who have discovered these three reactions, chemical reactions, being extensively used in modeling Okay, so when you do CFD modeling, you need to model how the pollutants are forming, and this is one of the important model that is used to capture the NO formation in internal combustion engine. 3 simple reaction steps. So first one, chemical reaction 1 is called rate controlling reaction, because in the first one you could see that nitrogen radical is formed from the stable nitrogen molecule. So you have a stable nitrogen molecule. As I just now said, it is inert. It's it doesn't participate in a chemical reaction readily because it's very stable with a triple bond. To break the triple bond, you need a very high energy, now known as activation energy. That's why the first reaction is an endothermic. You need to provide sufficient thermal energy for this reaction to take place. That's why we say that high temperature bond gases is a source. High temperature bond gases is a source for forming thermal NO. So at high temperature, typically around 2000 K or above, stable nitrogen molecule will be broken down and nitrogen radical will be formed. So, and this formation is triggered by, you could see that there is a O radical. O radical triggers nitrogen radical formation from nitrogen molecule. Okay, and this is an endothermic reaction, happens at high temperature. Once nitrogen radical is formed, you know any radical is chemically active. You could see that reactions 2 and 3 are taking place with nitrogen radical. It is oxidizing with oxygen molecule as well as with OH radical. Nitrogen radical is oxidizing, forming further NO. So reaction 2 and 3 are exothermic. They take place very quick. Okay, and once this N radical is available, 2 and 3 reactions, which are exothermic reactions, they take place quickly. So that's why we say that the reaction 1 is a rate controlling reaction. If you could avoid chemical reaction 1, then you can control this NO formation in internal combustion engine. So basically, we say that when we are able to control the operating cylinder temperature, you will be able to control the nitrogen oxide formation. That is NO, which is nitric oxide. Nitric oxide formation can be controlled considerably. So later on, I'm going to discuss with you one of the current technique that we adapt to operate engine, IC engine at a lower temperature, and we could observe almost 0 level of NO with this understanding. So we are able to run an engine at lower temperature. We primarily target chemical reaction 1, which happens at high temperature. We want to bypass or avoid this reaction. By doing this, we are able to achieve almost 0 level of NO. So anything that increases temperature, for example, fuel injection timing, when you inject the diesel fuel early, you are going to start combustion early. When combustion gets started early, in-cylinder temperature is high. So early injection, because of high temperature, contribute to high NO formation, thermal NO formation. And one of the popular, one of the popular NOx control method is EGR. So you recirculate exhaust gas back into the cylinder. Okay, by doing this, you are actually controlling this cylinder temperature. You are reducing cylinder temperature, and thereby you are avoiding thermal NO formation rate. Formation rate of thermal NO is controlled when you control the temperature. This is what you do with EGR. Later on, we are going to discuss about these control methods. Okay, emission control method, but understanding this mechanism, formation mechanism, is very important to devise a suitable control strategy. So for prompt NO, the NO is forming within the flame, okay? Within the flame, that is how it distinguishes from the previous one, thermal NO. So you have a flame formed, this is a chemical reaction zone. You have a flame, and within the flame, what you will have is several radicals, okay? Radicals are formed from the fuel. Fuel as such is stable. When combustion happens, the fuel break down and form several radicals. So within the flame, you will have considerable proportion of the CH2. These are radicals, C, carbon. These radical combine with nitrogen. Nitrogen is the flame. You present engine have these radicals available, N or Cn. This SCN or Cn are again an intermediate radical to a higher concept before the NO formation. Okay, and this is formed from CH or CH2 radicals which are present in fuel. So this intermediate nitrogen containing radical oxidize with the help of O and OH either O radical or OH radical, will oxidize HCN, and thereby it leads to forming N, okay, within the flame zone. And the contribution of this is only 10%, primarily due to the reason that you have a very thin flame in IC engine, both SI and CA engine. The flame will be very thin. Okay, the typical size is indicated here, 0.1 mm, 1/10 of an mm is a size, typical size. Why it is so thin? Hello?
Yes, sir. Yeah.
Why the flame in engine, IC engines, why the flame is so thin? I've given a typical dimension here, 0.1 mm, which is 1/10 of an mm. Because of the thin flame, what is happening is the time available for chemical reaction to take place within the flame, which is called as residence time. Residence time is too short. Residence time is too short. Because of the shorter residence time, the contribution of prompt NO is only 10%, as indicated here. But it all starts when you have a thick flame. When you have a thick flame, it will generate more NO. Since the flame is thin, it is generating only less NO because the time available for NO formation is very limited. Also, the area, flame area is less, so you are forming only less NO within the flame. That is what is the prompt NO. Now, the question is why not the flame be thick? Why it is thin?
So, flame propagation is very fast, very rapid here, sir. So the flame will be thin.
No, that is about flame velocity you are talking. But what I am saying is what is influencing here is not velocity, rather the flame zone area, thickness of the area. Thickness is very, very small. So you are, because of this, fortunately, the NO formed within the flame is less. But we need to know why it is a very thin flame. Okay, what is a possible reason for this?
Because the burned gas will try to expand, so it will compress the flame towards the burned gas.
Basically, it is going other way. The flame is compressing the gas. Flame is compressing the unburned gas. That is what is in SI engine is happening. The burned gas will push the flame. It will expand and it will move the flame at a faster rate. Like you said, the flame velocity is dependent on the burned gas expansion. The reason for a thin flame is in IC engine combustion, both SI and CA engine combustion, the engine operating pressures are very high. Okay, the pressure will have a considerable influence on the thickness of the flame. Since we run engine at a high pressure condition, okay, in atmosphere, if you look at an open flame, for example, a candle flame or a flame which is formed from any other source under ambient condition, pressure and temperature condition, you could see a thick flame, right? Have you noticed the flame zone will be thick? Have you seen any flame under ambient condition, atmospheric condition? For example, a candle flame or any other flame under ambient pressure and condition, you could see that the flame is, the area of the flame is considerably high, right? So this is because the pressure is less here. Whereas in IC engine, the operating pressure, both in SI and CI engine, the operating pressure is considerably high. When you expose flames to such a high pressure, you will have a thin flame zone. This is exactly the reason why we have a very thin flame zone. And fortunately, from a NO perspective, it is good because we are not generating more NO within the flame region, since the region itself is less. Third one is fuel NO. So the NO is formed from the nitrogen present in the fuel. Fortunately, the nitrogen content in fuel is less than 0.1% for diesel. For gasoline, it is nothing, we can ignore. Okay, in diesel, it is there, but it is less than 0.1%. And one thing here that distinguishes from NO formation through this route is it happens at a relatively low temperature, as I said, because the fuel bound NO is very active, unlike the nitrogen present in air. Because of this, this N present in fuel can react and produce like what we have discussed for prompt NO. So the formation step is almost similar. What we are seeing here, first intermediate nitrogen containing compounds will be formed, and this compound will oxidize with O or OH, creating NO. That is how the fuel NO is forming, fuel bound NO is forming. Okay, and the concentration is very low or negligible due to this reason. Next, we have this NO2. NO2 is nitrogen dioxide. So in NOx, X is either 1 or 2. Okay, so X1 is NO and X2 is NO2, nitrogen dioxide. We don't have NO3 or NO4, something like that. We have only these two oxides. Collectively, they are referred to as NOx, NO and NO2. So we have so far looked at how NO formation is taking place, what is the mechanism involved. Now we are looking at, going to look at NO2, nitrogen dioxide mechanism, formation mechanism. So you have two simple reaction steps. So reaction 1 is the formation of NO2, formation step. Reaction 2 is called decomposition of NO2, the decomposition step. So what is this formation step? You could see that NO, which is formed inside the cylinder, based on the mechanisms we have discussed so far, is going to react with this HO2 radical. HO2 is called hydroperoxyl radical. So this HO2 radical is available in IC engine. In any hydrocarbon combustion, you will have this HO2 radical. You have sufficiently high proportion of HO2 radical available in the cylinder. Because of this, the NO that is formed in the cylinder will react with HO2. In fact, it is oxidizing. NO is oxidizing to NO2. It is forming nitrogen dioxide from nitric oxide and then a OH radical. Okay, so this NO2 is formed basically due to oxidation of NO with this HO2. This is a reaction that is causing NO2 formation. This is the formation step of NO2, nitrogen dioxide. So what is also happening once the NO2 is formed in the cylinder, this NO2 is reacting with O radical, oxygen radical. Okay, oxygen radical is an active species which is also available in the cylinder. So this NO2 combined with O and form NO. So you are actually getting back NO. NO2 is formed initially in the first step. The second step, NO2 is getting back to NO with the availability of O radical. O radical availability is based on in-cylinder temperature condition. When temperature conditions are high, you will have a high O radical available. Okay, and whatever NO2 formed in the cylinder will get back to NO. So what I want to convey here is the conversion of NO2 to NO, which is called decomposition reaction, is primarily dependent on the availability of O radical. And the availability of O radical is dependent primarily on the temperature levels in the cylinder. When temperatures are high, O radical availability will be high. This is what is happening in a spark ignited engine. In a spark ignited engine, the operating temperatures are high. Due to high operating temperature, when I say high, it is high compared to diesel engine. So here I am comparing the operating temperatures of SI and CA. So for example, for a same power rating, T will be less, operating temperature will be less for CA engine, operating temperature for SI engine will be high. We already discussed about this. What is the reason for this? Hello? Why the operating temperature of SI engine is high?
Because of rich mixture, sir. 5 value is
0.9 to 1.2.
So this is primarily due to operating fee range. Operating fee is 0.9 to 1.2. Operating fee range for CA engine is 0.4 to 0.8. So you always have a overall lean mixture. Okay, global equivalence ratio is lean. You have more air. Because of high air availability, there is something called a quenching. Quenching of bond gases will take place in CA engine. Okay, because of this quenching, all this chemical reactions generally happen during the expansion stroke. Okay, during expansion stroke, there is a volumetric expansion. Piston moves away from TDC, volume increases, pressure will drop, and there is an associated temperature drop. This temperature drop during expansion stroke is high in CA engine because CA engine operating fee is low. And you always have XSR available in diesel engine, 30 to 50% XSR available in diesel engine. All this will result in reduced O radical availability during the expansion stroke of CA engine. Whereas in SI engine, you have a high operating temperature due to the operating P range that is close to rich mixture. That is where the max temperature will happen. So you always run close to max temperature condition. You don't have XSR, much XSR here in a SI engine. So the temperature drop during an expansion stroke when volumetric expansion of piston happens is relatively much lower in SI engine compared to CA engine. Due to this high temperature that is available during expansion stroke, the O radical availability is ensured, due to which whatever NO2 formed through the first step is going to get back to NO in SI engine, whereas in CA engine, getting back to NO is difficult because you have a problem of lower temperature or quenching effect, something like a quenching effect where the bond gases mixes with the excess air and the temperature of the bond gases is going to come down. Okay, this reduces the O radical availability. That is how the NO2 concentration is high in CA engine. As I said, it is around 10 to 30%. And this 30% high value will happen at low load condition. At low load, since you are controlling load in a, how do you control load in a CA engine?
By amount of fuel.
Fuel injection, mass of fuel injection.
Yes, fuel. So you have a Phi value much lower at low load because you have a less fuel that you inject at low load. So Phi is much lower at low load. So you can expect that the NO2 concentration is very high, up to 30% in diesel engine at low load condition. At high load, since you are increasing Phi, the temperature will be relatively high at high load condition compared to low load condition. So the O radical availability is increased. So as the load increases, the NO2 is going to drop in diesel engine, but at low load it's going to be high. Whereas in SI engine, as we have discussed, the NO2 concentration is less than 3% always, because you always have, irrespective of load, you know that you are running SI engine at almost a constant Phi at all the load, right? This is also another difference in SI engine operation compared to CA engine operation. In all the load, you are almost keeping same Phi value, which is not the case in SI engine. The CA engine, the Phi is going to be increased from low load to high load, whereas in SI engine, Phi is almost maintained constant at all load. Then how we are controlling load in SI engine?
Throttle, sir.
Throttling. So you are basically controlling or regulating the mixture quantity, okay, rather than quality. I think if you recollect, initially I said SI engines are quantity governed engine, CA engines are quality governed engine. You vary, quality means fuel or mixture quality. That is going to be different at different loads in a CA engine, because you control load through varying injected fuel mass. In SI engine, it is not so. You are not controlling load by varying the injected fuel mass. Rather, you control the quantity of the mixture that goes into cylinder using this throttle valve. Okay, so because of this reason, you almost maintain a constant Phi, which is close to stoichiometry or slightly rich, which will result in high operating temperature. And O radical availability is ensured. That's why NO2, whatever formed in the cylinder, will get back to NO in SI engine, resulting in overall NO2 levels less than 3%, which is not the case in CA engine. Clear?
Yes, sir.
Okay, so so we have so far discussed about this NOx formation mechanism, NO and NO2 formation mechanism. Now we are moving to discuss about CO formation mechanism. CO is again a pollutant both in SI engine and CA engine. In general, SI engine CO levels are very high. We have discussed that. CA engine CO levels are low, primarily because whatever reason we just now discussed. SI engine operating Phi is close to stoichiometry or rich, even rich. So that is causing high CO levels up to 200 gram per kg, typical concentration levels we have discussed. In CI, the levels are less. You have excess air. Okay, oxygen availability is ensured in CI engine. So one of the primary reason for CO, you know, CO is partially oxidized carbon. the fuel we'll deal with are gasoline and diesel, which are hydrocarbon fuels. What is the carbon content in gasoline and diesel? We discussed this in chapter 1.
So around 85%.
Yeah, around 84% is the carbon content, both in gasoline and diesel. So we have a high carbon fuel that combusts, and this high carbon fuel cannot always form CO2. This is complete combustion. What what this carbon will form is CO, which is a pollutant. It's a toxic gas, as we have discussed in the health effects. This needs to be controlled. Okay, it is a toxic gas. So partial oxidation of carbon present in the fuel is going to form CO. Complete oxidation of carbon is going to form CO2. Okay, so what could lead to partial oxidation? The primary reason, as you can think of, is insufficient oxygen. When oxygen levels are high, CO is going to get oxidized to CO2. When oxygen levels are low, CO can only partially oxidize. It cannot completely oxidize. Okay, and this is happening with rich mixtures. So rich mixture is a source, primary source for forming CO, because in rich mixtures, you have oxygen deficiency. Insufficient oxygen will result in partial oxidation of carbon, leading to high levels of CO in the engine exhaust. So the primary source or cause for forming CO is rich mixture with Phi greater than 1. And SI engine run up to 1.2 or so, and you have a uniform high Phi levels inside the cylinder, which is what is causing significantly high CO in SI engine compared to CI engine. The other source, I would say this is relatively a minor source that result in CO, is through dissociation reaction. Dissociation is a chemical reaction, endothermic reaction. CO2 levels in the engine cylinder, if at all it is high, and if the temperatures are high, the CO2 is going to absorb high temperature and get dissociate to CO and half O2. It's going to dissociate, form oxygen and carbon monoxide. Okay, so CO2 can dissociate when temperatures are high. This is an endothermic reaction. Any dissociation reaction is an endothermic reaction. Combustion is exothermic reaction, it releases thermal energy. Endothermic reaction is opposite, it absorbs thermal energy. So when you have sufficient thermal energy in the cylinder, CO2 is going to absorb the thermal energy, dissociate, form CO and O2. This is another source, and this can happen even with the lean mixture as indicated here. Wherever you have high CO2 level, wherever you have high temperature available, CO2 is going to dissociate, which can happen even with lean mixtures. Okay, so what I want to highlight here is not only rich mixtures, lean mixtures can also form CO depending on the prevailing temperature, operating temperature. But the primary source is rich mixture. This is where the CO levels are going to be high. So when you talk about CO, there are two things here that you need to keep in mind. That one is the formation rate. So inside the cylinder, there is a mechanism. I'm going to briefly discuss about that. There is a mechanism that results in forming CO due to partial oxidation. Okay, so there is a CO formation happening in the cylinder. The rate of formation of CO is very important because you know the time available for engine operating cycle is limited, and it depends on the engine running speed. And these reactions are happening during a fraction of engine operating time. Total time, a fraction of the time is devoted or available for forming the CO. So there is a formation rate. I use the word rate because this is a time control, time bound, driven by kinetics. So there is a formation rate of CO, and apart from, the total CO that is formed in the cylinder, a considerable fraction of CO can also get oxidized. So there is something called oxidation rate of CO. So whatever CO formed in the cylinder can also get oxidized to CO2. Okay, so you have a formation rate, you have an oxidation rate. The net CO that goes out in the engine tailpipe is a resultant of these two reactions, and both are time bound, kinetically driven. Both the reactions are kinetically driven. I will briefly discuss about the kinetics involved in forming CO and oxidizing CO. But the point to be noted is there is a formation rate, there is oxidation rate. So you have to subtract the CO oxidation rate from the formation rate to get the net CO. That is what is coming out in the engine tailpipe. So this is a formation mechanism. It all starts with something called hydrogen abstraction. R is any hydrocarbon radical. Any radical is active, as you know, as we discussed in the chemical kinetics chapter. So you will have an active hydrocarbon radical formed in the cylinder. You have this R available. Okay, CO formation takes place by removing an hydrogen atom, from this radical. As you could see here, RH leads to forming R. This is called hydrogen abstraction reaction. Once hydrogen is removed, you could see that this R will react with oxygen. This is available in the cylinder and form RO2. Okay, peroxy radical. This is RO2, and RO2 leads to RCHO, which is an aldehyde. This is again a radical active species that leads to RCO. Okay, acyl radical, and finally from RCO you are getting into CO. This is a step, chemical reaction step, that leads to forming CO from the stable fuel molecule. Fuel has 84% carbon. Okay, when you know, when fuel is subjected to combustion, initially you know the stable fuel will break down into several molecules, and this some of these are active radical species. Okay, this radical species during the chemical reaction step of fuel combustion is forming the CO through these reaction steps. Okay, and it all starts with hydrogen abstraction. And this can very well take place with gasoline and diesel. Hydrogen abstraction reaction is going to take place, and through that you finally get into CO. Whatever CO form in the cylinder, a fraction, considerable fraction, in fact, considerable fraction of that CO is going to get oxidized to CO2. So there is a mechanism that governs the oxidation of CO to CO2. This is an important chemical reaction step that leads to CO2 formation from CO. CO is oxidized to CO2 in the cylinder itself. CO is a pollutant. CO2 is currently not a pollutant. You see here that CO oxidized with the help of OH radical. So one of the important radical that you need to have in the cylinder to oxidize CO is CO2. When you have sufficient OH radical available in the cylinder, you're going to convert CO into CO2 in the cylinder itself. So CO control is easier then. So you also have to ensure that you are able to oxidize the CO in the cylinder itself. Then it will reduce the burden on the after treatment control system, which we are going to discuss later on. Okay, so CO is converted to CO2 by reacting with OH radical, and one more H radical is formed. This reaction can take place in the forward direction or in the reverse direction, as indicated here, depending on the concentration of OH radical and H radical. So for the reverse reaction to happen, you need to have a considerably high proportion of H radical. If you have a considerably high proportion of H radical, then the reverse reaction will take place, forming CO, which is undesirable. Instead, if you have a high proportion of OH radical available in the cylinder, the forward reaction will take place and CO is going to get back to CO2. So the way this chemical reaction proceeds, whether it may be a forward or a backward, it depends on the concentration of or the availability of OH and H radical. That's why we have this 3 rate controlling reactions, which is going to decide the concentration of OH and H. If you look at the first reaction carefully, you could see that 2 H radical combine in presence of M. M is the third body, and form a stable H2 molecule. Similarly, second reaction, if you look at H radical combines with O2 in presence of a third body and forms HO2 radical. Okay, so here two reactions are destroying the H radical. So this will ensure that there is a less H radical available, which will favor the reaction to move in the forward direction, because H radical concentration is reduced through this reaction 1 and 2. Rather, if you look at the third chemical reaction, H is combining with OH in presence of third body and forming a stable H2O molecule. So this third reaction is actually killing this OH radical. It's reducing the OH radical availability, because you could see that for CO oxidation, we need OH. Because of the third reaction, if at all it happens at a faster rate or at a higher rate, you are going to reduce the OH radical level. When this is reduced, you're going to, this forward reaction is not favored. We use the word favored. Forward reaction is not favored because OH radical availability is reduced. So these three chemical reactions control or ensure H or OH radical availability, thereby it is controlling the oxidation reaction. The primary oxidation reaction is this, but in this reaction, you have two important radicals that decides forward or backward propagation of reaction, okay? And those OH and H radical availability is ensured based on these three chemical reaction steps. Clear? So that is the reason why we say that CO level in the exhaust is kinetically controlled, because there is a mechanism that governs oxidation, there is a mechanism that governs formation rate. The final net levels in the engine exhaust is based on both formation rate and oxidation rate. Okay, so we have so far discussed about the CO mechanism, formation mechanism. Next, we are moving to HC, unbound hydrocarbon formation mechanism. Unbound hydrocarbon formation mechanism, unlike NO2 and CO, which are kinetically driven, we already discussed that this is not kinetically driven, rather it is based on boundary layer fluid dynamics. How the flow happens in the boundaries of engine cylinder is going to decide the concentration of HC in the IC engine. Because of this reason, the mechanism is different in SI engine and CI engine. HC formation mechanism is going to be different in spark ignited engine and compression ignited engine, because it is based on the boundary layer fluid dynamics. NO and CO formation mechanisms are going to be same for SI and CI engine. The reason is they are kinetically driven, and the kinetics are going to be same both for SI engine and CI engine, whereas the flow, boundary layer flow, is not same for SI and CI engine. That's why the mechanisms are different for SC formation. The first thing we are going to start with is SI engine. We are going to look at here how the unbound hydrocarbon is formed in a spark ignited engine, what kind of boundary layer dynamics govern the unbound hydrocarbon formation. This is what we are going to look at. And the other important information that you need to note down here is, when I say unbound hydrocarbon, it is not one species. Rather, you have around 400 species emitted from internal combustion engine, both SI and CI engine. It's a multi-component mixture. This mixture, everything put together, is what we are referring as unbound hydrocarbon. It's not one species like CO or NO. Okay, it's not only one species. Rather, it's a mixture of species. Okay, and the number may be as high as 400 species. Why do we have such a large number of species? Everything put together is what we are collectively called as SC. Why do we have such a large number of species from IC engines?
Sir, so because of presence of higher number of species in fuel itself, sir.
Exactly. So we burn gasoline in SI engine. We burn diesel in CI engine. We have discussed about the molecular composition of gasoline and diesel in chapter 1. They are multi-component mixture. I said that the number of hydrocarbons in gasoline and diesel can vary between 100 to 1000. 100 to 1000, such a complex fuel, both gasoline and diesel. So they are mixtures of hydrocarbon. So when we say unbound hydrocarbon, the source is fuel, right? When you use a complex fuel with different hydrocarbon, you are going to get different species as indicated here as an outcome. And these species are not oxidized completely. Unbound hydrocarbon is either partially oxidized or unoxidized. So this is either partially oxidized hydrocarbon or unoxidized. Unoxidized in the sense completely misses the oxidation or combustion. It's through misfire. So either it is partially oxidized or unoxidized, unoxidized fuel. That is what is a hydrocarbon. Suppose if we use a lot of alternative fuels also, right? For example, gasoline, instead of gasoline, you can use ethanol or methanol. We will briefly discuss about that later on as a pollutant control method. So when you use a simple fuel, single component fuel, accordingly, the complexity of unburnt emission is going to be less. Rather, gasoline and diesel are complex multi-component hydrocarbon. That is the reason why the hydrocarbon species are complex, because the fuel itself is a complex mixture. Okay, and out of this total mixture, some of them are partially oxidized or unoxidized. That is what is leading to HC formation. We refer that as an unburnt emission from IC engines. Okay, so in SI engine, we have already discussed about this plot. If you recollect how the operating fee influences HC emission, we already discussed for all the three pollutants from SI engine. HC, this is a trend we discussed. So one is stoichiometry. When you move towards this region, it's lean. This region is rich. So when you move towards lean, you could see that there is a drop. There is a drop in pollutant HC in the engine. Whereas when it passes a threshold limit, say here in this case, I have shown 0.8. Okay, when you move further down below 0.8, you could see there is a sharp increase in HC emission. Because when you move towards a lean region, you will have something called misfire, because the flame stability is going to be poor in the lean region. Overall combustion in SI engine is a flame stability, flame propagation based event. This is what we have discussed. It's very difficult to maintain a stable flame when you move towards a lean side. Okay, so you may completely miss the combustion because the flame, you cannot maintain stable flame when you move towards lean region. This is what is causing misfire. That is the reason for the sharp rise in HC emission when you move towards 0.8, below 0.8. Okay, so lean region, you will have a very high HC due to misfire because you cannot maintain a stable flame. And this is exactly the reason why we have a narrow operating range in SI engine. Flame stability is poor beyond this region. Either in the rich side or lean side, you cannot maintain a stable flame when you move out of this zone. That's why you have a narrow fee zone in a spark ignited engine. Primary consideration is flame stability. Otherwise, you cannot maintain a stable flame. So on the lean side, you will have a misfire problem. When you move towards rich mixture, obviously you are seeing a rise in HC, and this is due to insufficient oxygen. When you move towards rich region, the oxygen availability is reducing. Right? When you move towards too rich region, there will be considerable rise in the HC formation because oxygen is reducing, and you cannot oxidize all the hydrocarbon species present in fuel. Okay, so gasoline, you have a range of hydrocarbon. You cannot oxidize all this hydrocarbon when oxygen availability is reduced. So you will have a sharp rise in unburned hydrocarbon emissions. In fact, HC emission from SI engine is higher compared to CI engine because you are running towards a rich region with less oxygen. That's the reason for very high HC from SI engine compared to CI engine. CI engine will ensure oxygen availability with lean mixture. Okay, so on the rich side, the problem is insufficient oxygen that causes HC formation. On the lean side, you will have poor flame stability leading to misfire. That is what is causing a high rise in HC emission. So both lean mixture and rich mixture can cause high HC formation in a spark ignited engine. This is an important information you need to note down. Apart from this, there are various sources for HC formation. Okay, as indicated here, crevice flow, flame wall quenching, adsorption and desorption in lube oil and carbon deposits, liquid fuel entry into engine cylinder, bulk quenching. And the number on the right hand side shows the total contribution of these particular source to the HC emission. For example, if you look at crevice, this alone contribute to 40% of the total HC formation. So it means this source is going to be a considerably influential source for forming HC emissions in a spark ignited engine. It's time up. I stop here. We will continue this in the next class. If you have any questions, you can ask. Are there any doubts?
No, sir.
For the hydrogen radicals, we mentioned that code is R. It's only for that hydrogen or other radical mix that species. It's also with the same hydrocarbons.
So you are talking about this
The yes. R.
400
R.
species. 400 species. Yeah, some are without oxygen, some are with oxygen also. There are some oxygenated hydrocarbon species also. For example, aldehyde, CHO.
Yes, addition to the representation we mention as a R. The symbol is R.
Sir,
It is in
Ah,
CO form.
Symbol R is any hydrocarbon radical.
Okay.
Any hydrocarbon radical. When I say radical, it is an active species. When a stable molecule breaks down, it leads to forming different hydrocarbon species. And some of them are active radical, and they are represented by using this general symbol, R.
Okay.
Okay. Anything else? Fine. So I'll stop here. Tomorrow is a holiday according to your calendar. So I will meet you on Wednesday. We'll meet on Wednesday, 6 o'clock. Tomorrow there is no class according to your calendar due to holiday. Okay.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you,
Bye.
sir.
Thank you.
Thank you.